Okay, our next talk is by Robert Tang. We'll be talking about coarse and fine geometries of saddle connection graph. So,
okay, thank you very much, Alex, and thank you to all the organizers for putting on this great marathon. Okay, as I mentioned, I'll be talking about the saddle connection graph and focusing on both its coarse geometry and fine geometry aspects. And before I begin, I should mention that everything I talk about is based on joint work with Valentina Disarlo, Huiping Pan, and Anja Randecker. Okay, so let me give you an outline of the plan for today. Okay, so first I'll begin with some backstory. So introduce some old characters that you may have seen before and maybe some new ones, tell you a bit about those. Okay, so in particular, the saddle connection graph is the main character I want to talk about today. Then I'll talk a bit about its Theorem of boundary. What does that mean? Can we interpret it in a nice way? And then the main part of this talk is looking at the saddle connection graph from the point of view of isomorphism classes versus quasi-isometry classes. Okay, and towards the end, if I have enough time, I will give you some ideas about how we go about the proofs. Okay, so let's begin with some background on what are sort of commonly known as combinatorial complexes. Okay, so to begin with, we're working in the world of topological surfaces. Okay, so for me, for this context, I'm always going to assume that I have some finite genus closed compact surface with a finite non-empty set of marked points. Okay, so that's what I'm interested in. And first we can define the arc and curve graph. Okay, so I need to tell you what the vertices are and what the edges are for this graph. Okay, so let me just show you what a curve is. So for me, a curve is going to be something like this. So an embedded copy of the circle that is not, that cannot be homotope to one of the marked points. And I want to consider these up to isotopy. Okay, so if I slide it around, I consider it to be the same. I can also consider arcs. And my requirement for arcs is that the endpoints have to be at the marked points. Okay, and then again, I'm allowed to homotope them around, but the endpoints must remain fixed at all times. Okay, so the objects in the arc and curve graph are going to be either curves or arcs. I am not going to allow any arcs that you can sort of shrink and pull back to one point. So that's the non-trivial assumption. And the edge relation to such objects are adjacent if you can isotope them so that they are disjoint. Okay, so just to be a bit careful here. So in the case of arcs, I allow this to be considered disjoint. As long as the interiors is disjoint, I'm happy. Okay, but what I don't want is, for example, this blue arc. They're allowed to start and end at the same point. So this blue arc will intersect this pink one. So they're not adjacent in the arc and curve graph, whereas the orange and the blue one are adjacent. And each of these guys are also adjacent to this curve. So that's the arc and curve graph. Okay, so I'm considering everything up to isotopy or proper isotopy. And then once I've defined this, I can define both the curve graph and the arc graph, which is just going to be the subgraphs spanned by taking the set of all arcs, or the subgraphs spanned by taking all curves. Okay, so that's those three definitions in one. Okay, so this is just an induced subgraph on some set of vertices. All right, so what have these things been useful for? Okay, so in geometric group theory, when you want to study groups, very often you want to find some nice spaces on which they act. And if you can show that these spaces are hyperbolic, then you can use a lot of the useful tools from studying hyperbolic groups. Okay, so these three graphs they do share these properties. So in each of these cases, the arc graph, the curve graph, and the arc and curve graph of a surface, there are some caveats for low genus exceptions, but in most cases, they have the following properties. These graphs are connected. They are locally infinite, which means that the degree of every vertex is infinite. And they also have infinite diameter. So this is when we're using the combinatorial metric, where we measure the distance between two vertices as the length of the shortest path connecting them. Okay, so using that metric, these graphs have infinite diameter. And as I mentioned earlier, the most important property is that these are Gromov hyperbolic. Okay, so I mentioned groups. So the main application for these complexes is to study the mapping class group. Okay, so the mapping class group of a surface is the group of all homeomorphisms of the surface back to itself. When we have marked points, I need the marked points to be mapped bijectively. Okay, and these will be considered up to isotopy. Okay, so in the case of marked points, you want isotopy that preserves the marked points at all times as well. Okay, so it's not hard to see that the mapping class group acts on each of these graphs. Okay, because what you need to know is that if two curves or arcs were disjoint to begin with, if I apply a homeomorphism, they will remain disjoint afterwards. So we get a natural action of the mapping class group on each of these graphs. The non-trivial thing, the important thing is that, in fact, these are all the possible automorphisms. Okay, so the first theorem was proven by Ivanov for the curve graph. So this is sometimes called Ivanov-style rigidity. Okay, we know that we have a group acting on this nice geometric space, but the very nice thing is that those are all the symmetries. So the automorphism group of such a complex is isomorphic to the group you're interested in. Okay, so that's a much nicer property than just having a group acting on a space. Okay, so all right, so that's the background on the topological setting. So what I'm focusing on in this talk is something where you have some geometric structure. Okay, so I'm going to talk about translation surfaces. For the experts, you might have seen half translation surfaces, but I'll just ignore that for this talk. So what is a translation surface? So it's a surface that has a type of locally Euclidean geometry. Okay, so I'm just going to give you an example of how you can construct one. So suppose I give you a regular Euclidean octagon in the plane. And then what I can do is I can glue opposite sides by translations. Okay, so when you do this topologically, what you end up with is a genus 2 surface. Okay, and the corner actually gets identified. So these 8 corners eventually become identified to give you a single marked point. Okay, so I'm going to assume that when I do this, my singularities will be treated as marked points. Okay, those are somehow like the different points here. Okay, and here when you glue this up, you got like 3 pi on 4 at each angle, and you got 8 of them. So when you glue up together, you get an angle of 6 pi around the singularity. Okay, so that's an example of a translation surface. The word translation means the gluing mass by translations. I also allow half translations, which means you are also allow a rotation by pi in the gluing maps. But this example does not show it. Okay, so there are some nice facts. So as I mentioned, locally, you have a Euclidean metric. So away from the singular point, there's a nice flat geometry. The cone points would be multiples of pi because I'm only ever gluing by translations or half translations. And the important thing is that there's a global notion of slope. Okay, so if I have a vertical slope, if I do a translation or rotation by pi, this always stays vertical. Okay, so if I follow this, for example, this yellow line, if I go through here and come out this side, it stays parallel to itself. Okay, if I keep going, that remains true. So if I keep going and traveling, if I never run into a singularity, this trajectory will never self-intersect. Because if it self-intersects, it has to be non-parallel. Okay, so that's a nice thing about these translation surfaces is that they have a consistent notion of slope. Okay, so as opposed to sort of more general Euclidean cone surfaces where you can just glue them up in by isometries in any way you want. Okay, so as I mentioned before, I was looking at the curve graphs and arc graphs. So when you start putting some geometry on the surface, okay, then there can be some arcs or curves that are more interesting than others. Okay, so a fact about translation surfaces is that they have a locally cat-zero metric. So what that tells you is that if I given any isotopic class of an arc with fixed endpoints, there's a unique geodesic representative in that class. Okay, so for example, I can consider these 2 arcs, topological arcs in yellow and red here. Then if I pull them tight to the geodesic representative, I'm going to get something which is sort of so the typical situation is this red one where it might be a sequence of these straight line segments. So it will be like a sequence of Euclidean straight line segment connected singular points followed by another. Okay, a single straight line segment connecting singular points is called a saddle connection. Okay, so some arcs, when you straighten them to its geodesic representative, will just use one saddle connection. So these are the special ones that I'm interested in. But the more typical situation is when you pull them tight, they might run over many, many saddle connections and possibly multiple times. Okay, so I'm going to focus attention only on the arcs that can be represented in this way. Okay, if when you pull them tight, they're represented by a single straight line segment that goes through no other singularities. So the saddle connection graph, by definition, will have the vertices represented by these sorts of arcs. and you have the same edge relation as for the arc graph. Okay, so what I get is basically a subgraph of the arc graph. Okay, I take a subset of vertices and take the induced subgraph of that. Okay, for that to make sense, I always had to make the standing assumption that the set of marked points is identified with a set of singular points. Okay. So there's a very nice fact about this embedding. As a result of Minsky and Taylor, is that the embedding. So okay, just this notation SQ. So stands for S with this half translation or the translation structure. So Q for the expert stands for quadratic differential, but we don't need to worry about that for today. Okay, so you have this saddle connection graph. It embeds into this arc graph. Okay, and the main thing is that this is an isometric embedding. So the distance is measured in the saddle connection graph equals the distance measured in the arc graph. Okay, and as an immediate consequence, this shows that the saddle connection graph is both connected and also hyperbolic. Okay, which is nice. All right, so let me maybe give you a very simple example of one of these saddle connection graphs. Okay, so I'm going to consider the once marked torus. So a torus with one marked point, and we all know we can construct a torus by taking some square and gluing opposite sides together. Okay, so I can think of this purely topologically, or I can think of this square as an actual unit square with the Euclidean metric. Okay, and if I do this, okay, I get a locally Euclidean metric on the torus where this corner is going to be treated as my marked point. Okay, and a fact about the torus is that actually every arc, it corresponds to some rational slope, possibly infinity, and actually every arc can be straightened to a single straight line segment. So in this case, in this very special case, the arc graph and the saddle connection graph actually coincide. Okay, so every arc can actually be straightened to a single straight line segment on the flat torus. So it's the same graph. There's nothing different here, but generically for higher genus, these are not the same graphs. Okay, so maybe more explicitly, here's the picture. So every arc on the torus can be sort of recorded by the slope, a rational slope. And if you represent these by rational numbers, there's a rule telling you whenever two slopes have intersection one, so it's like P over Q and R over S are adjacent. If and only if you got this, I think PS minus PR has, no, not PR, QR, this determinant like quantity is equal to 1. So there's a way of measuring the intersection number between two slopes on the torus by this formula. Okay, so using this rule, you can figure out exactly what this graph is. So this is known as the fairy graph, which you sort of have this nice picture. You have these triangles that expand out like this. Okay, so I'll come back to and talk about the fairy graph maybe in a bit later. Okay, so those are the main objects. The saddle connection graph is the thing I'm interested in. So how is it like, or how is it different from the old objects, the arc graph or the curve graph? Okay, so when we have a Gromov hyperbolic space, it makes sense to talk about its Gromov boundary. Okay, so the Gromov boundary, just quickly, is you can identify it with the set of geodesic rays starting from some base point up to some fellow traveling equivalence relation. So if two rays travel forever, then they're going to be considered equivalent. Okay, so there's an old result of Clareich, which identifies the Gromov boundary of the curve graph with something called the space of irrational topological foliations. Okay, so in some sense, if you think of, say, some sequence of curves, okay, so this is on the curve graph. If you imagine some sequence of curves going up to infinity, they'll sort of get more and more complicated. So if you start drawing curves that sort of get really messy on the surface, they'll start to look like they have like infinite length and just go sort of everywhere. So in the limit, sort of intuitively, you get this thing called a foliation, which basically it's something which looks like you're just partitioning the surface into this like locally straight lines or some curves that look like this. Okay, so it doesn't matter what they are. The point is that there is some meaning to the objects at infinity. Okay, so irrational here means that they intersect every curve non-trivially. So that leads us to a natural question. Okay, so we know that the saddle connection graph, so we can also prove that the embedding into the arc curve graph is also an isometric embedding. And what is true is that the arc and curve graph and the curve graph are quasi-isometric. So that tells us that the Gromov boundary of the arc and curve graph and the Gromov boundary of the curve graph are the same, or they're homomorphic to one another. Okay, so the fact that this isometrically embeds into the arc and curve graph means that the Gromov boundary of the saddle connection graph embeds into this set here. Okay, so then there's a natural question is, okay, well, this is going to be a subset of the set of irrational topological foliations. So a natural question is like, well, which foliations arise from the boundary of this thing? So this is some subgraph. It's going to give you some subsets of which foliations arise when you do this. Okay, so it turns out there's a natural answer. So we can answer this question. Okay, so the foliations which arise on the boundary of the saddle connection graph are exactly the straight foliations which contain no saddle connections. So what do I mean by straight foliation? Well, there's a local Euclidean structure on the surface, so it makes sense to say that a leaf is straight. Okay, so if I give you a certain slope, I can foliate this translation surface by lines that are parallel to that slope. Okay, so that will give me a foliation where all the leaves are parallel. And the condition is that, okay, there are no leaves that form saddle connections that go from one singularity to another singularity. Okay, these are sort of sometimes called the arational slopes. Okay, so it's like so it's basically saying it's like these are sort of the infinite sort of limit versions of saddle connections in some sense. Okay, they have to remain compatible with the Euclidean structure, but they're sort of also kind of an infinite version of these things. Okay, and we can characterize when a sequence of saddle connections converges to some point on the Gromov boundary. It's precisely when the corresponding slopes converge to some slope which is arational. Okay, so arational here just means that it's not a slope of a saddle connection. Okay, so in the example of the torus, we saw that all the saddle connections had the slope which are rational. So the arational slopes are exactly the irrational numbers. Okay, in that example. Okay, so next, so that's the Gromov boundary that has sort of a nice answer, which is sort of not too surprising if you're familiar with this sort of area. So next, I want to go back to this talk about this sort of theorem of Ivanov. So there are a lot of complexes related to topological surfaces such as the arc graph, the flip graph, the marking graph, the Pans graph, and so forth, which have this nice property that actually the mapping class group is isomorphic to the automorphism group. Okay, so specifically for the arc graph, this is also true. So if I give you two arc graphs, so for topological surfaces, and an isomorphism between the arc graphs, then that isomorphism has to come from an actual homeomorphism between the surfaces. Okay, so here the homeomorphisms have to send the mark points bijectively to one another. Okay, so every isomorphism between graphs is actually meaningful topologically. Okay, so then we can ask the same question about saddle connection graphs. Okay, if I give you two saddle connection graphs, I don't know what the underlying surfaces are. I don't know what the genus of those are. Can I say anything about those two surfaces? Okay, so we have an answer to this question. So this was done independently by myself, Valentina Disarlo, and Anja Randecker, and simultaneously by Huiping Pan. Okay, so indeed, every isomorphism between saddle connection graphs is induced by homeomorphism, but not just any homeomorphism. It's induced by what's known as an affine diffeomorphism. So let me just give you an example of what that is. So it's not just a homeomorphism. It's going to be a homeomorphism which sort of looks like this. So I'm not going to give you the precise definition. Just look at this example. If I take this translation surface defined by this polygon, and I apply some element of GL to R, I'll get some deformed polygon. But you can see that GL to R will preserve parallel sides, and these line segments will remain the same length. Okay, so the gluing pattern stays the same. So what I've done is I can map this surface to another surface which is homeomorphic, but has a different metric on it. Okay, but these metrics are going to be affine equivalent. Okay, there's some affine map from one surface to another, which does this. So maybe it's not hard to see that if I give you a saddle connection here, well, affine transformations preserve straight lines. So this thing will stay a saddle connection over here. So one direction is going to be the easy direction. If I have an affine diffeomorphism from one translation service to another, you get an isomorphism between the saddle connection graph of this one to the saddle connection graph of the other one. What we proved is that the other direction is true, that all such isomorphisms between the graphs must come from something geometric. Okay, and furthermore, we show that the group of all affine transformations from a surface to itself is isomorphic to the group of automorphisms of the saddle connection graph. All right. So what are some consequences is that if you know the isomorphism type of the saddle connection graph, then that gives you a complete invariant of the affine equivalence classes of translation services. Okay, so that's all the affine information you want is in principle encoded by this graph. And consequently, there are uncountably many isomorphism classes of saddle connection graphs. Okay, so this is because there are some high dimensional moduli spaces of these translation services that you can study. Okay, so this is different from the topological setting where you really only have countably many homeomorphism classes of surfaces. They're really only determined by, say, genus, number of mark points, number of boundary components, and so forth. Okay, so that's something that's different here. We get uncountably many different isomorphism classes. Okay, so we still have this sort of nice rigidity, but there's like a much finer distinction between them. Okay, so the second theme in my talk is going to be about quasi-isometric rigidity. So what can we say about knowing about these objects up to quasi-isometry or quasi-isometries of these objects to themselves? Okay, so let me just quickly define the quasi-isometric group of our metric space. So this is going to be the group of quasi-isometries of some metric space to itself after this notion of equivalence, okay, where two such maps are equivalent if they sort of agree up to finite distance. Okay, so there exists some constant such that like f of x and g of x are always within that distance for all x. Okay, so that's sort of sometimes it's called a closeness or like finite distance. Okay, so otherwise this group is going to be too huge. Okay, so a metric space X is called quasi-isometrically rigid if the natural map from the isometry group to the QI group is an isomorphism. Okay, so isometries are themselves quasi-isometries, so there's a natural map here, but this is saying that every quasi-isometry is going to be finite distance from an actual isometry. Okay, you can't really do anything interesting other than taking the isometry and just sort of perturbing it by some bounded amount. So this QI rigidity is an interesting property and has been shown to hold for many of these objects related to surfaces and mapping class groups. So the curve graph satisfies this property. It's QI rigid. The mapping class group with its web metric has also been shown to be quasi-isometrically rigid, and also Teichmüller space with I think the Teichmüller metric and the Weil-Petersen metric. So it seems like for any sort of reasonable object attached to services, this QI rigidity seems to be a thing that happens. Okay, and another related property is that, okay, also proved by Rashi Schleimer is that the quasi-isometry type actually completely determines the isomorphism type of the curve graph. So what they show that if I give you two curve graphs and all I know is that they're quasi-isometric to one another, they show that actually these graphs actually had to be isomorphic. Okay, and in most cases, isomorphic curve graph implies homeomorphic surface. So you go from something really, really coarse to get something really, really fine. You actually tell a lot from just the quasi-isometry type. Okay, so this again gives us a natural question. What can we tell from the quasi-isometry type of the saddle connection graph? Okay, so following on this theme, well, it turns out that the answer is absolutely nothing. You can tell nothing at all from the QI type of the saddle connection graph, which is, I guess, quite surprising when we first discovered this. So our main theorem is that for any translation service, if you look at the corresponding saddle connection graph, there's an explicit quasi-isometry to the regular infinite valent tree. They are all quasi-isometric to one another, and there's explicit constants here as well. We actually construct an explicit quasi-isometry from any saddle connection graph to this tree. So in this case, there's only one QI class, which is like completely different from isomorphism classes. We have like uncountably many isomorphism classes, but only one QI class. Whereas for the curve graph, the QI classes and the isomorphism classes were actually the same. So this is sort of like telling us some kind of very different behavior. When we start to look at geometric structures, we may not expect the same things to happen as for what we saw in the topological situation. So as a corollary, we can quickly show that the saddle connection graph is not QI rigid. So how can we see this? Well, we know that the saddle connection graph is QI to the infinite valence tree. Okay, so the QI group of the saddle connection graph is isomorphic to the QI group of the infinite valence tree, and this group is uncountable. Okay, so like if you know about automorphism groups of regular trees, you know that these are uncountable groups. Okay, but the automorphism group, okay, this is, we showed in our previous result that this is isomorphic to the affine diffeomorphism group, and this is a subgroup of the mapping class group of the corresponding surface, which is countable. So there's no way for the, well, this is basically the same as the isometry group of the graph. There is no way for the isometry group and the QI group to coincide just by looking at cardinality. Okay, so that's a corollary showing that we don't have QI rigidity for the saddle connection graph. Okay, so in the remaining time, I don't know how much time I have, but I'll talk about how we actually construct this this map here. So how do we construct this quasi-isometry from the saddle connection graph to this tree? So the way we do it is that we construct a quotient map of graphs. Okay, so just a reminder, how do you construct a quotient map? Well, basically you define an equivalence relation on the vertices. So when you do the quotient, your vertices are going to be equivalence classes, and two equivalence classes are adjacent if there exists some vertex here adjacent to some vertex here. Okay, so you partition the vertex set, then you have a quotient map which sends each blob to a vertex, and you have the edges if there exist ones here. Okay, and a simple lemma is that if you know that every equivalence class in the partition has bounded diameter, then the quotient map will be a quasi-isometry. Okay, so with explicit constants. Okay, sort of if each blob is sort of uniformly bounded, then you crush them from a point of view of coarse geometry, they're going to look the same. That's the intuition. Okay, so we don't directly work with the saddle connection graph. In fact, we pass through an intermediate graph, which makes things easier to work with, called the graph of slopes. And this is going to have similar features to the fairy graph. So the graph of slope is just going to be the quotient graph we get by identifying parallel saddle connections. So the set of vertices are going to be slopes of saddle connections. So like in the case of the fairy graph, we're just going to be taking rational numbers. But in a more general case, if you have these three saddle connections which have slope 1, they'll be identified in the quotient graph. Okay, they'll be identified with the slope of 1. You can have horizontal and vertical ones. They'll give you different ones as well. So the nice thing is that with parallel saddle connections, they're disjoint. So they're going to be adjacent in the saddle connection graph. So this immediately gives us a 2-1 quasi-isometry from the saddle connection graph to the graph of slopes. Okay, so the nice thing here is that we can sort of pretend that the vertices of the graph of slopes are points on RP1. So we can identify with numbers or infinity and draw the graph on this circle as points and imagine that we have edges going in here like the fairy graph. Okay, but we're not going to expect this to be embedded. Okay, so the strategy for constructing this quotient map is to find a partition of the vertices of the graph of slopes, and to prove that the equivalence classes are going to be bounded. We show that the diameter is almost 17, and that the corresponding quotient graph is isomorphic to what we want. Okay, so that's what we're going to do. So let's go back and take inspiration from the fairy graph. So the guiding principle is that we're going to pretend that everything is in the fairy graph. So what are some features of the fairy graph that are useful? So in the fairy graph, I want to understand, like, say, what the balls look like from a base fixed from a given point. So if I look at infinity, while all the vertices are adjacent to infinity, well, those are just going to correspond to the integers. Okay, everything adjacent to infinity are going to be the integers. So the integers look something like this. Okay, then at the next step, I want to look at, okay, what are things that are distance 2 from infinity? well, those vertices are going to look like this. So I'm going to go step out from each of these integers and sort of go like that. You're going to get some infinitely many things like this. And if I go distance 3, then I'm going to sort of step out like this. So what I want you to observe that every time you increase the radius by 1, okay, if I delete these points from the circle, I had one big interval. Once I deleted the integers, this interval got subdivided into infinite many subintervals. And every time you increase the radius by 1, each of these subintervals again gets divided into infinite many again and again. So what we show is that the same thing actually happens in the graph of slopes. Okay, so we can look at balls in the graph of slopes. So like here, I'm just going to pick some base point. I don't know which one. And I'm going to set bk to be the radius k ball around that vertex. So these results are going to be non-trivial, but they should remind you of what happens in the fairy graph. So the ball is going to be some set of vertices. So if you consider this to be a subset of the RP1, it's going to be closed. So we've shown that this is a closed set. So it's closed and countable, which means it has a measure 0. So the complement is going to be some nice union of open intervals. Okay, you don't have like some dense set where you got like rationals or something. Okay, the complement is nice. It's going to be some countable union of open intervals. So then I can look at this sort of post set of intervals. I can start off with like, say the interval at distance 0, I get 1. Then I get the intervals at distance 1, so I get the subdivision and so on and so on. So IK will be the connected components when I delete the slopes that come at radius k. Okay, and I would just be this post set of all these intervals. Okay, and another lemma is that, okay, indeed, when you go at radius k and you add in the slopes that are at distance k plus 1, each such interval again gets subdivided into infinitely many. Okay, so there's infinitely many new ones that get born at each step. Okay, so sort of the picture here is like when you subdivide, okay, you have infinitely many each time, okay, and then you subdivide again, you get infinitely many each time. Okay, so this is like when, say, k equals 0, k equals 1, and so forth. So this post set of all these intervals, if you look at the Hasid diagram, okay, we actually get this tree T infinity. Okay, that's where this T infinity comes in. We have one vertex at the top, it has infinitely many children. Okay, and each of these children has infinitely many children, and so on and so on. Okay, that's where this tree-like structure comes in. Okay, so then how can we use this tree-like structure, this intervals, to come up with a partition of the graph of slopes? Okay, so what I'm going to do is like, hey, suppose I give you an interval in RP1, well, then I can define a subset of the graph of slopes, which is just all the vertices where the slope lives in that interval. So remember, a slope is both a point in RP1, but also a vertex of this graph. Okay, so I can consider the subset of these vertices where the slope is in that interval. So for every such interval, I can define a subset of vertices in the graph of slopes. And we can show that for any such interval, the subgraph spanned by the vertices in maybe in some interval is going to be connected. Okay, so there's a connected subgraph associated to any such interval. Okay, but you can sort of say that this is not going to give you a partition, because if I give you one interval contained in another, the corresponding subgraphs will be contained in one another. So that won't give you a partition, but there's this tweak that we do that gives us a partition. So I'm going to give you some subset of the vertices in one-to-one correspondence with each interval. So for the initial interval at distance 0, I'm going to define this set, which is the ball of radius 3. And then for every interval which sort of arises in later generations, I'm going to take this graph GI, okay, the slopes which have those vertices, but I'm only going to take those at distance exactly 3, k plus 3 from the origin. Okay, so that's sort of make sure that different levels are going to be disjoint. Okay, so we have this sort of big blob in the middle, and this is sort of a schematic picture of what the partition looks like. So what we show is that indeed, the quotient graph is isomorphic to infinity. Okay, so that amounts to showing that there's no stray edges connecting these blobs. Okay, that the only edges that are between blobs are the ones that we want to be there. And secondly, we prove that each blob, each slice has bounded diameter. Okay, and all of these actually use a lot of the flat geometry involved in the surface. Okay, so putting these together, once we have this nice partition, we can conclude that the quotient map from the graph of slopes to T infinity is a quasi-isometry, a surjective quasi-isometry with explicit constants. Okay, so probably I'm running over time, so I will not talk about this part here. So maybe I'll stop now. Okay, thank you.
Thank you. Let's just conclude it. Are there any questions?
Yes, explicit constants. Yes, everything in our construction is explicit. We write down the map. We also proved that the saddle connection graph is 4 hyperbolic, which is better than the known constants for the arc graph. Yeah.
Okay, are there any more questions? If not, I'll end the recording now. Okay, let's take the speaker again. And I'll end the recording.